Alright, and here we are again in series RCL circuits. This time we are going to look at what happens when our incoming frequency is what we refer to as resonant frequency. So what that is it's a phenomenon where the frequency makes the ohmic value of your two reactive components, so your XL and your XC, equal each other, so they are the same value. Alright, let's take a look at that formula for that. And here is that formula. You'll see it labeled as FO. It's not unusual to see resonant frequency labeled as FR. And all you do is take your inductance, multiply by your capacitance, square root the answer, and then multiply it by 2 pi. And then invert it, take 1 over it. And that will give you resonant frequency. Now in this case, resonant frequency is 22.91 kHz. So the first thing we do is start with our ohmic values for our two reactive components. Now in actuality, if we knew that we got our resonant frequency correct, we would only have to do the ohmic value of one, and that would tell us the ohmic value of the other. Because remember, resonant frequency causes those two ohmic values to be the same. So we look at our inductor, and we have an ohmic value of 10.07 k ohms. Now we are going to have the same ohmic value on the capacitor. If I put those numbers up, we see we have that same 10.07 k. Alright, impedance is interesting. I'm going to throw that formula up because I want to talk about it for a minute. You will notice the impedance formula. There's your resistance, your 10k. But you will notice where your ohmic value for your inductor and your capacitor goes. I put those up. They are the same. So if I take 10.07 k and I subtract 10.07 k, I get 0. And 0 squared, square rooted, it's still 0. So in actuality, the entire formula exists with just the 10k from our resistance. Now if you square and then square root 10k, you get 10k. So there's actually no point in even doing the formula. Impedance is resistance in a resonant circuit. And this particular circuit only has one resistor, but it doesn't matter if they have multiple resistors. You'll just combine the resistance. But resistance will be impedance in a resonant circuit. Okay, current is easy. All we do is take our voltage divided by our impedance, and we get, in this case, 4.5 milliamps. And all that's left now is voltage. So for our resistor, we take our 10k multiplied by our current of 4.5 milliamps and get 45 volts. Now the interesting thing about your voltages on your two reactive components, they're going to be the same, of course, because their ohmic value is the same, their current is the same, so you would have to get the same voltage. But they are going to be canceling each other out. If you think about Eli and ice, if you think about your graph for Eli and ice in a series circuit, the constant is current. So if I make current where I am pivoting off of, and I look at the I that is common to both of them, I see that voltage for my inductor leads by 90 degrees, and voltage for my capacitor lags by 90 degrees. So at any particular time, my two voltages are 180 degrees out of phase. So they cancel each other out. And then if you were to put your meter in that, you would see that as well, because of course your meter reads red minus black. If both leads have the same value, you're going to see 0. Alright, so let's do the math real quick. So the voltage on our inductor is 45.32 volts, so the voltage on our capacitor is going to be the same. And then you'll see that same thing we were talking about here in this voltage formula. You'll see the voltage on the capacitor minus the voltage on the inductor, or vice versa. It really doesn't matter. But you'll notice that because they have the same voltage, we're going to have 0 there. And we're going to come into the same scenario that we had up in impedance, where we have 0 and it doesn't matter because if you square and square root it, you still have 0. So actually what we end up with is the voltage on our resistor. So we always find that when we have a resonant circuit, we see applied voltage on our resistor, or resistors if it happens to be the case. Of course, in this one there's only one. So we see our applied voltage on resistor 1. And here's the rest of that math for you to see. All right, we are going to look at another circuit similar to this one, but I changed the numbers up. This one, everything was so close, it doesn't really give you a good idea of what resonant circuit can really do in a series circuit, or resonant frequency can really do in a series circuit, and I wanted to kind of give you a look at voltage magnification. So we're going to do another video on this one. You'll see the whole process again.